Okay, in our final structure of the atom video, we're going to look at stimulated emission and lasers. So stimulated emission is the process that we need to produce a laser. And as you've probably guessed, we're talking more about light. This structure of the atom topic is much more about light than the atom in many ways. Okay, to understand how a laser works, we need to first understand the concept of stimulated emission. There's a number of concepts in this slide which might seem new, but I think if you just persevere with it, you'll see they all actually go together fairly neatly and they're not too confusing. So firstly, we're just going to consider a case where we've got a very simple atom with just two energy levels. So we know that if we put energy into an atom, we will get this concept of absorption that'll put that atom into a excited state. And then what would normally happen to that atom in the excited state is it would undergo what we call spontaneous or ordinary emission. It would relax and it would release a photon of light. So that's what we've sort of looked at so far with line emission spectrum. Okay, but now we want to consider an atom that's actually already in an excited state. So this atom is already in an excited state. We have an energy level difference here, E. Now, if a photon comes along with energy E, so this energy here corresponds to this energy level gap here, what this will do is it will stimulate the atom to relax. So it will relax like such, but something really, really neat and special happens here. When that happens, we get produced two identical photons. And when we say two identical photons, we mean that they are going in the same direction and they have the same phase, and I haven't said this, but obviously they have the same frequency and wavelength. So if you like, this process of stimulated emission almost photocopies the photons and it produces two identical photons. Same direction, same phase, same frequency and wavelength. Hopefully you're starting to go, aha, that's sounding like laser light, coherent light, all in the same phase, monochromatic, and obviously laser light points in a single direction. So obviously just this happening once won't create laser light. We need to have this, get this to happen over and over again. And that's what we're going to explore, how we achieve that now. So we've covered here this process of ordinary emission, stimulated emission. And now, how do we make this work in a laser? Well, firstly, we need to create what's called a population inversion. And a population inversion is produced in a set of atoms whenever there are more atoms in a higher excited state than a lower energy state. So if we go back to these two here, we need more atoms in the excited state, or this one here, the excited state, than in the ground state. Because if there's more in the ground state, when this light hits, it's more likely to cause an absorption to a higher energy level than to cause a stimulated emission. So we need to create some scenario where we have most atoms here in this higher energy excited state. So we call that a population inversion. So I think this is just repeating what I just said. If photons with energy corresponding to the transition from the higher energy state to the lower energy state are incident on a set of atoms in which there is a population inversion, there will be more stimulated emissions than absorptions. So if we've got more like this in an excited state than like this in the lower energy state, there'll be more stimulated emissions than absorptions. Now, some excited states last for relatively long periods before they undergo transition into a lower energy state by spontaneously emitting a photon. These are called metastable states. So if we want to create a situation where we've got lots of atoms in an excited state, we actually need a long-lasting excited state to create. So we need to find an atom that has one of these metastable states, one of these relatively stable higher energy states, so that we can excite the atom somehow and create a situation where lots more are excited than are in the ground state. So, for practical systems, that is to make a laser, the higher energy state must be metastable, must be a metal stable state if a population inversion is to be produced. So we've got if we want to make a laser, we need to find something that's got a metastable state. Otherwise, we won't be able to create a population inversion. Lots of things I just said there. If you're still a little bit confused, just watch over this one a couple of times. But I think hopefully it'll start to become clear. Cheers. Okay, so now we're going to talk about how we actually build a laser, in this case a helium neon laser, and how we make use, or how we come up with a practical scenario where we can use stimulated emission to produce laser light. So I'm going to talk about the energetics of the process first, then I'll talk about the literal physical components you need to put into a laser to build them, and then finally we'll just talk about some of the important uses and safety requirements of dealing with lasers. So what we have in a helium neon laser, which is the example we're going to look at, is we have a mixture of helium and neon gas. And the reason we choose these two is firstly, neon has a metastable state at about 20.66 electron volts. So that's a long-lasting excited state. And helium happens to have a very similar energy level gap between its ground state and its first excited state. So this is the third excited state for neon. So what happens is we excite neon by putting energy into the system, and then when neon gets excited, it gets pushed up here into this excited state here. Then the neon has a little bit of kinetic energy as it's moving, and it collides with the helium, has a little bit of kinetic energy, and it collides with the neon, and it transfers energy in that collision. And when it transfers its energy, it puts the neon into this metastable state. So we can end up here now with our population inversion, because we've got lots of atoms going into this third state, which is obviously a higher energy than the second state, and because it's longer lasting, they stay there for a reasonable amount of time. So then, initially we might just get one spontaneous emission, if you like, to get the process going, you might think of, but let's assume that's happened. And we have photons coming along here, and the energy of these is 1.96 electron volts, which if you do the conversion works out to be red light, the correct wavelength. And that strikes these atoms in this metastable state, and it produces two identical photons, which is basically what we require for our laser. So, what are the actual practical components we need to make this process here happen? Well, firstly we need an active medium, and in this case that's the helium and neon gas. We need a pump to supply the energy to excite the atoms initially. So we need some sort of pump, probably should have that in inverted commas, and in most cases that will be an electrical discharge. So it'll apply a voltage across the gas, and that will cause the helium to get excited, or obviously a different gas if it was a different type of laser. And the third thing is we need mirrors at each end to amplify the laser light. So basically we've got our laser light being produced in this region here, and they're going backwards, forwards, backwards, forwards, backwards, forwards mostly. And by going backwards and forwards, they're colliding with more excited neon atoms and producing more and more and more identical photons. And then we just let a small amount of those photons out through basically a lens here. And that's the laser light that we see. So in here, they just keep bouncing around to produce as much of this light as they possibly can, so that we can get our small beam of it coming out here. So they're basically the three components that we need to build a laser. And finally, we'll just touch on some of the uses and some of the safety issues with lasers. I think you should probably all be fairly familiar with these. We'll do safety first. We should always do safety first. Obviously, laser light is very, very high intensity, has a very, very high intensity, and it can easily damage sensitive tissue, particularly things like your eyes. So to be very careful about pointing lasers in people's eyes. We've already talked about a number of the uses of lasers in this course, LADs, CD and DVDs. They're also used in things like barcode scanners at supermarkets for laser surgery, particularly on eyes, and also in things called laser cutters and engravers. That's one near to my heart at the moment, because we've just written a grant to try and get a laser cutter for our school. I know the guys at Roxby will be very familiar with the one up there. So that's it for the structure of the atom, aka let's learn about how light is produced. Cheers.